So far we have discussed what is convex optimization problem and what is gradient descent algorithm with constraint set and without constraint set. And we also analyzed the convergence rate, the rate of convergence of gradient descent algorithm with proper step size gamma. So the first case was when the objective function is convex and the objective function is ellipsis continuous. So in that case, when we set the step size gamma is equal to x0 minus x star distance over square root to t times the ellipsis continuous constant L, then we can show that the convergence speed proportional to 1 over square root capital 1 over square root t. So the distance to the optimal point fxt minus fx star is proportional to 1 over square root t. That was the first result. And the second case was the case beta smooth, where the optimal step size was 1 over beta, and we have basically 1 over t convergence speed. And if we have more strong assumption, the function is beta smooth and alpha strongly convex, then the result becomes more powerful. Basically the convergence speed, so still the step size is equal to 1 over beta, but the convergence speed is roughly 1 minus alpha over beta power to t. So I think this is the most easiest case we solve. So with a few iterations, we can easily reach to the optimal point x star. And this is the most difficult case where we need a lot of iterations. For instance, let's consider this case fx0 minus fx star is let's say 1000, and we want to make xt minus fx star less than or equal to 1. So 1 is kind of our error margin. So we can allow amount 1 error. So to achieve less than 1 error, we have to learn 1000 square iteration basically when the function f is ellipsis continuous. And if the function is beta smooth, then 1 over beta running rate, we just need 1000. And if the function is alpha strongly convex and beta smooth, and alpha and beta is close enough, so basically then we can achieve less than 1 error rate with a few iterations, because the learning the error proportional to this one. So the error exponentially decrease and the conversion speed even faster when alpha and beta are close to each other. Okay, so basically your optimization problem becomes more difficult when alpha and beta has some huge distance. When alpha and beta close to 0, then your gradient descent algorithm convergence speed may be very slow. And this is the case where the contour looks like this, very narrow valleys. So here, this direction has very high gradient partial derivative value, but this direction has very tiny partial derivative value. So for this direction, good running rate may be very small, but for this direction, the good running rate must be very high. Otherwise, the gradient or partial derivative to this direction is very tiny, with very tiny running rate and gradient, you just move very tiny amount. So to reach to this optimal point, you require a huge number of iterations. Okay. And also in the previous lectures, another difficulty when you learn gradient algorithm is the case when we have constraint set. So we have discussed projected gradient descent algorithm. So here every time we compute xt plus 1 by projection, and we denote by this one by yt plus 1. And the projection operation required to solve another optimization problem. So we have to find argument between x and yt plus 1 among all your constraint point. And this is another constraint convex optimization problem. And sometimes this is not easy to solve, especially when x shape is not simple and x has very high dimensional space. Then this problem also very difficult to solve. Okay, so this week I will introduce some technique, and that techniques useful for some cases.